Hi, I'm David Nguyen, and thanks for visiting my poster. So my project is about a new way of measuring order and disorder in tumors, and how this can be applied as a new diagnostic tool to improve precision medicine. To start, the architectural organization of cells inside a tumor is highly disorganized, such that most people would say that the arrangement of cells is random. However, there's a difference between randomness and disorder. When we say that a system is random, what we are saying is that what we're assuming is that we have sufficient knowledge of what is non-random in that system, such that we can say that, oh, this tumor, the cells are arranged randomly. However, from engineering computer science, we know that the entire premise of encrypting email and digital information that's sent over the internet, right, is premised upon our ability to actually make something, something that's ordered to look so disordered, right, that it's, incomprehensible and thus sort of random. Okay, and so there is existing evidence, if you look at Figure 1, that tumors do have an inherent order to them that we have been aware of for a long time. This is why tumors can be graded by a pathologist as grade 1, grade 2, or grade 3, being the most, say, aggressive. And the grading system of tumors is based upon features such as nuclear morphology, the pink or purpleness of the hematoxylin eosin stain in the tissue, and other factors. And furthermore, pathologists are able to classify tumors according to their histopathological subtype. For example, a pathologist can identify a tumor as, an adenoid carcinoma, while another tumor might be a, cystic, right, carcinoma. Another one might be metaplastic. Okay, so metaplastic carcinomas or metaplastic breast cancers are ones in which the structure, architecture within a tumor, right, is highly variable, as in it's not just one type or one recurring type of structure, it's multiple ones mixed together, right? So it's very hard to, can be very hard to classify a metaplastic tumor, right? But the fact that there is tumor grading and histopathological subtypes, right, is strong indication that though tumors are highly disorganized, right, there are recurring themes and regularities that scientists can identify and use to stratify cancers into varying degrees of, say, aggressiveness or severity. So the purpose of my research is to refine that ability such that we can classify these tumors even further into more specific groups. That allows us to then determine which types of tumors respond to therapy better, what type of therapy, and which type of tumors ultimately relapse more than others. In order to do this for metaplastic tumors, I created what's called the Quadrant-Slope Index. So in order to, if you look at Figure 2, right, the way you would do the Quadrant-Slope Index, or QSI, is to divide the entire image into a grid of uniform squares, okay? And then each of these squares you then further divide into 4 even squares, right, with a two-dimensional XY coordinate. And so when each of these within each of these XY quadrants, right, or each of these squares has 4 quadrants, right, that result from an XY axis, right, you can simply trace the longest length of each nuclei, right, and the slope of that line will either point up, right, be positive slope, or point down, be a negative slope, right, with the bottom of the image being the reference, okay, the horizontal x, parallel with the horizontal x-axis. So in this way, in each of these quadrants, you can count the number of upward slopes and the number of downward slopes, okay, and such that you can divide a one over the other, right, such as in Figure 2C. In this way, not only can you generate a number, okay, for each quadrant that is in each of these squares in the larger grid, right? These numbers can also be turned into a color, right, in the form of a heat map. So in this way, by the Quadrant-Slope Index method, right, you can generate a new view of a tumor image. If you look at figure 3, here's a hypothetical example. In figure 3a, here is typically a cartoon of what a metaplastic tumor would look like, right? This is a garbled arrangement of cells of different types and orientations. In figure 3b, here's a hypothetical grid that has been created, and each of the red axes, right, is one of the squares in the grid of the whole tumor. All right, and each of the quadrants resulting from the red axes, right, can become a color. So in this way, if you look at figure 3a, right, it was purposely drawn to have an obvious pattern of cells in the upper right-hand corner of 3a. That is these spindly, stretchy, elongated cells that flow together, like a stream of water, say, a stream of liquid, okay? And so that's sort of easily detected by the human eye, and also by the Quadrant-Slope Index method, right, as seen in figure 3c, right, the green squares, right, labeled as O for obvious, right? However, a lot of people are surprised that there's another hidden, order in figure 3a. That is the bottom right-hand corner, right? You have these oval-shaped cells that are arranged in a row, right? But to the human eye, it's really hard to pick that out, okay? Especially if you're looking under a microscope, as pathologists do, or now even on the screen, as pathologists in the United States are allowed to diagnose, according to the FDA now, this several months ago, diagnose tumors and tissues by looking at computer screens, right? And so, so people are often surprised to realize that, wow, yeah, so figure 3a does have two regions of orderliness, right? The obvious one and the letter H in 3c, figure 3c, that is the hidden, right, region of order, right? And so that's the power of this quantitative method, the Quadrant-Slope Index, in that because it is calculated with the help of a computer that can, calculate things very quickly and, at a high rate, we're able to turn the features, right, the orderliness and disorderliness of a tumor into numbers, okay? And furthermore, we can aid the pathologist by visualizing the degree of order and disorder, right, in each tumor. Right? So this allows for more refined stratification of tumors. Okay, instead of just grade 1, grade 2, grade 3, we can create grade 1A, 1B, 1C, 2A, 2B, 2C, etc. Right, and so this is exciting in that this method has the potential to enhance the precision diagnostic oncology, so that when your physician takes a biopsy of your tumor and sends it to a pathologist, the pathologist can give a more specific recommendation as to the stage of your disease, say, and which therapy would best help you with the fewest side effects. It's also exciting in that, the next stage is to test whether, if we hand calculate the QSI instead of use a computer, what is the minimum number of QSIs or squares, right, in a tumor image that we can calculate and still accurately predict the outcome, right, of that that patient, that sample. That would be highly useful in the case where people can only have access to low-tech diagnostic tools, whether that's in the case of developing nations or when the hurricane shuts down electricity, right? And our batteries, our apps, our computers run out of electricity. What do? Right? Then we have to rely on the old school method of just pen and paper, so to speak. And so when we have a large, there are a lot of large archive data sets of tumor images that also correspond with the patient data as to age and disease stage and how long they lived and how long they lived before relapse happened, right? Such clinical information. And so having that data, we can perform the QSI measures and create a benchmark, right? A table such that somebody who whether they calculated the QSI using computer or by hand, they have a table in which to interpolate, right, the severity of a patient's tumor, right, and what the recommended treatment options are, right, in light of the QSI index, right. So this is very exciting, and we are in the process of testing this on breast cancers, but it is applicable to many other types of cancers and even normal tissues that are non-cancerous, but have an affected morphology due to disease exposure or some other challenge or insult, as it is referred to by scientists. So that's a summary of my talk. Thank you for listening. Feel free to reach out to me. My email address is dhnguyen@lbl.gov. Okay, that's the end. I think I went over. I'm at